output layer, then we will calculate this way to determine whether or not this y will corresponding to a class. So if you have an input as features of cats and dog, you want the output to be just cats and dog. Okay, so that's the one example we can apply for classifying the cats and dog using the simple neural network. But you might imagine that it's not enough. So for the deep neural network, it's simply we just put more neurons and more layers. And so for this case, there are lots of calculation need to be done for the deep neural network. So that's why we need powerful computers. And don't worry, so I think the computer you have right now is already powerful enough. So you don't need supercomputers, but just usual computers, we can already do this type of job. But for deep neural network, there are some problems. I will illustrate in later the lower half of this class. Okay, so just try to understand that for the deep neural network, we have more than one layers. So we may have 3 layers, even the hundreds layers. That is possible. And we still the output layer is the class. So you can apply this model to classify cats and dogs, and only 2 outputs here. Okay. So probably the major breakthrough of the machine learning is the invention of the convolutional neural network. So convolutional neural network is not just a deep neural network. For example, you can see the right side here. And for these parts, it's actually the same with the deep neural network you see here. So for this part, you can just use deep neural network. But for the left part, you need to do something on images. So for example, this is a car images. Then we need to use some convolution feature extraction to extract the essential features from these images and to reduce the data dimension. So actually the convolutional might be very unfamiliar to you, but this words just is the process to extract the image features. And we just put these features into the deep neural network and to get the result. So the CNN is really a combination of the feature selection and the deep neural network. So that is the whole principle. So I will show you the detail in another class about this one. So let's make a very simple comparisons. So you can see that these are for these parts, these are the data containing the red dots and the blue dots, okay? So for the logistic regression, you can just plot a straight line to classify these 2 groups. But immediately you will see that, for example here, this red dot is classified. And also, this blue dot is classified. So if you are not satisfied with logistic regression, you can try to use decision tree. So just like I said, you can just cut in the different orientations and to make sure the cut or the separation will separate nicely about these 2 groups. And also you can use a nonlinear classifier like a support vector machine to draw a curved line to separate these 2 groups. Or using a random forest, which is very similar to this one, and you can just plot a very curvy, complex shape around these 2 groups. And also for the simple neural networks, actually it's very similar to the logistic regression. Actually, let's go back to this one. So you can see that for this one, the reaction of this neuron is very linear, right? It's just only 1 or 0. So that's why it's very similar to logistic regression in this case, because in a simple neural network, you just apply all or none functions to to this kind of data. So the performance will be very similar to the logistic regression. So if you have more than two data category, like three class of labels, then you can see that we need two lines to classify the data into three classes. And also you need a more complex way of decision tree to classify these samples. Also for SVM, you need to plot another shape to just separate these three groups. So for these old techniques, it's a very classical, and we will show you how to do different algorithms in different classes. So perhaps the other interesting part is the unsupervised learning. Okay, so for the unsupervised learning, then you want to classify like Mickey Mouse and Donald into different groups. So, but sometimes it doesn't make sense. So you need to know what feature you look at. So I want to show you one example I did in the very early time. So we know that each author has his own style, right? And for example, when you look at the novel from the different authors, you will feel that the writing style is different. And that is very subjective. Then how do we do this in an objective way? So that's what I did in 2003. So this is the case that we know that these books are from the Conan Doyle and also Conan Doyle, sorry, and also some novels are from different authors. So we can use an algorithm to do a classifications. So this is unsupervised learning because we don't already, although we know the answer of we know the author of these books, but we want to develop an algorithm to classify these books in the correct clusters. So how do we do that? For example, if you look at the plays written by Shakespeare, so Shakespeare wrote lots of the plays, and this is one of them. This is Winter's Tale, and the other is Cymbeline. So if you look at these two plays, they are all written by Shakespeare. Then what's the difference? So let's take a look. So first, you can calculate the number of the words in this play. For example, you can calculate the number of the word "the" in the play Winter's Tale. So there are 857 words "the" in this play. And likewise, you can also calculate the words "the" in the play Cymbeline, and there are 966 occurrences. So you can apply this calculation to all words appears in this play. Then to try to sort them by the frequency. So the first rank is the most frequent words. In this case, is the, and the second one is the I, and the third one is and, the to, of, you, and etc. So immediately you can see that the rank order of these words are very similar between the Shakespeare's play, right? When you compare the plays from different authors, so one is the Shakespeare, still the Winter's Tale, the other is the plays from the John Fletcher, which is Banduka, the play Banduka. You can see that the rank order is very different. So the first rank here is and, the second one is the, and the third one is I, and also it's very different from this one. So I use this rank order difference to make a plot. So we can just plot the rank order of these words in one play and compare this rank order in another play. So for the Shakespeare two plays, you can see that the rank order is very similar because they have a very similar occurrences. But for the comparison between the Shakespeare and Fletcher, is more scattered. So meaning that their rank order is very different. And using these features, we already developed a measure called distance measures. So for the unsupervised learning, the one important thing you need to to define is what's the distance between two objects. Okay, so for this kind of thing, you can define the distance between two texts or two places. But for the images, then you need to define a way to measure the distance between two images. That's a different thing. But for this one, I can just use the rank order statistics. So for example, for this comparison, you will intuitively see that the distance between Shakespeare and Fletcher is larger than the distance between Shakespeare.
管理中心报告，稍后将进行消防系统测试。稍后将进行消防系统测试。如有警铃鸣响，警铃鸣响，广播语音警报，广播语音警报，请住户不用惊慌，请住户不用惊慌。造成编之处，请予见谅。造成编之处，请予见谅。
Okay. So the distance between the Sibling and the Winter Snail is closer than that between the Sibling and Bandukas because these are represented the books from the two single authors, and this is from the different authors. So you can use this the relationship to build up this cluster analysis tree. So for this tree, we can see that the Sibling and Winter's Tale is under the same cluster, and the Banduka is in a different branch, and that helps us to differentiate this cluster from this one. And that is the important concept about the unsupervised learning, because when you have the data, then you don't know the underlying difference. So you can just define the distance and try to build up a cluster tree, and to see whether or not this new, for example, we want to find out the origin of the COVID-19 virus, or Wuhan virus. Then we want to compare the Wuhan virus and build up a tree here to see what's the position of the new virus in this kind of phylogenetic tree. So this is really about the phylogenetic analysis. We want to know the relationship between different species or different origins. And there are already lots of algorithms developed for this kind of test. So I think I already designed a class in probably 10 or 9 weeks. We will show you how to cluster the dementia patients using the EEG features. Okay. So that's one result I have done before, is that so if we have the plays from the Shakespeare, and also the plays from the John Fletcher, but we know that some plays are written collaboratively by the Shakespeare and Fletcher. For example, the Two Noble Kingsmen is written by the two authors. So both authors contribute to this play. Also, the Henry VIII also collaborate by the two authors. But the question is that if the one text is written by two authors, then how do we classify that? And interestingly, we found that Henry VIII is more closely related to the Shakespeare, and the Two Noble Kingsmen is written related more to the Fletcher. And we already know that the Shakespeare wrote the major part of the Henry VIII, and Fletcher wrote largely about the Two Noble Kingsmen. So that's the way we can quantify very objectively in this kind of data. And also in the medical data, we want to do the similar things. For example, we know in psychosis, there are 3 diagnoses. One is schizophrenia, and the other part is the bipolar disorders. And some may have just 2 symptoms. So for schizophrenia, they have hallucination, delusions, and for bipolar disorders, they have like mania, the emotional symptoms. But for some patients, they have both. They both have hallucination, delusions, and the symptom will continue for a long time, but at the same time they also have mood symptoms like mania or depression. So for this diagnosis, they are based on the symptom criteria. And the question is that, can we reclassify these patients into different groups? And one way we can do this is based on the cognitive functions. So we know that schizophrenia or bipolar patients, they all have a certain degree of cognitive decline. Their memory becomes worse, and their executive functions is not good as the normal person. So if we use the cognitive function or some like a test to classify these patients, then we can reorder them into 3 groups. So in this paper, they just say that, okay, we can reclassify them into the so-called biotype 1, or biotype 2, and biotype 3. And this classification is just based on the cognitive functions. And for this classification, you can immediately see that, okay, for the biotype 1, there are more patients of schizophrenia. Okay? For the biotype 3, there are more patients of bipolar disorders. And that is very reasonable because we know that bipolar patients, usually they have a better cognitive functions than those you're seeing in the schizophrenia. So if you use cognitive function to classify these patients, you will see this kind of distributions. So I want to use an example to show you that it's very important that what feature you want to look at. And if you use cognitive functions, you will find these clusters. If you use like maybe like mood symptoms, then you will see another type of clusters. And is that meaningful? I don't know, because we need to find a way to validate these clusters. So the difficult part about unsupervised learning is that you really need a way to validate your result. So this is the most challenging part in the machine learning. So let's talk about this in the case of Alzheimer's disease in the later course. But for now, we will focus on the supervised learning. So it's very intuitive. You just want to classify the data into 2 or 3 labels. Or you want to build a model to tell that whether or not a patient or EEG data has severe depression or mild depression. Or you want to build a model to tell that whether a data is corresponding to a measure. So that's the regression part. So the supervised learning can do many things. We can do classification, we can do regression, and this model can apply to many new data. So that's the most exciting part. And also, we need to know that there are some new developments in the machine learning fields. For example, when we learn something, then, for example, in the hospital, and we already learned how to diagnose patients. But sometimes we will encounter a difficult patient that we don't know what's the diagnosis, right? So we will do many things to make sure to find out the diagnosis. So for that case, we actually do the reinforced learning. So for example, there's an apple, there's an input, and the computer say, okay, it's a mango. Then we know it's the wrong answer. So we'll tell the algorithm it is not a mango, it is an apple. So the algorithm will try to modify itself, like modify the weights or modify the infrastructures, and so it will deliver the correct answer in the next time. So that is reinforced learning, and it is also a very hot area in machine learning right now. So I hope that I have time, we can show some example in a later time. And probably another important challenge is that you don't want just algorithm to be a black box. right? You want an algorithm to tell you, not only tell you the answer, but also tell you why. So for example, the famous competition of the Go between AlphaGo and the human is that we know that AlphaGo is very strong, but we don't know how it developed its strategy. So that is a challenge we need to solve in the future, because we really need an explainable AI, but not an unexplainable AI. So for these different machine learning algorithms, they have different explainability, meaning that if you have already did a regression before, then you will know that what I talk about. So for example, for the statistical models, usually we can develop a model to predict something, but also we will know that which predictors is important, right? So for the statistical models, usually the explainability is good, but they have a very poor, or usually have relatively poor accountability. So they have very poor accuracy compared to the deep learning. But for the deep learning, they have very high accuracy, but usually their explainability is very low. So we really need to develop a method to try to improve the explainability of the deep learning, so we can not only know the answer, but also know why the answer is. So that's it, the question. So I'll just make you an example here. So for sleep medicine, for sleep medicine, we have lots of data about the physiological signals. Then we want to differentiate the different sleep diagnosis based on these signals. So that's why we need something like computational sleep science. So for example, we need to derive the features in the EEG data or in the sleep data. Then we want to use these features to tell us what is the sleep quality or what is the sleep diagnosis. So that is the whole challenge here. So we don't want just results like the diagnosis. We also want to know that what feature contribute to this assessment. So that is the meaning of explainability. Okay, so the other interesting part about the artificial intelligence is the Turing test. So everybody hear about Turing test? So Turing test is named after Alan Turing. Alan Turing is a very famous computer scientist. Actually, he invented a very important part of the computer. So in the World War II,